Hey everyone, and welcome to The Explainer. Today we have something really special. We're celebrating Professor JS Chen of UC San Diego, who was recently awarded the prestigious John von Neumann Medal, a huge honor in our field. Now, this tribute was actually prepared by his former student, Mike Hillman, who himself has built on this legacy with methods like NSNI and VCI. So today, we're not just looking at one brilliant career, we're going on a journey to explore the thousand-year legacy that made it all possible.
So, what does the official citation say? It honors his seminal contributions to stabilized, mesh-free methods for simulating solids under extreme loads. And that is absolutely cutting-edge stuff. But here's the really cool part. These incredibly modern ideas are woven into a story that stretches back for centuries. This award isn't just an endpoint, it's a new milestone on a long, unbroken road of discovery. And that brings us to the big question we're tackling today. How on earth does a modern method for simulating explosions and impacts connect to someone studying the cosmos in the 13th century? I know, it sounds a little out there, but stick with me. We are going to trace the intellectual DNA of computational mechanics from Professor Chen's work all the way back through history and uncover an absolutely astonishing lineage of ideas. Okay, so let's start our journey in a place many of you will remember well, the 1990s. At the time, the king of computational mechanics, the finite element method, was starting to show some cracks. Its core strength, the mesh, was actually becoming a liability in certain cases. The stage was set for a revolution. So here's the fundamental problem they were facing. Look, FEM is a workhorse. It's brilliant for a lot of things. But when you get into really extreme stuff, we're talking impacts, fractures, things blowing up, that mesh, its greatest strength, becomes its Achilles heel. It gets twisted, tangled, and the whole simulation just dies. Mesh-free methods were like a breath of fresh air. Instead of a rigid grid, you just have a cloud of nodes. They can move freely, which means you can simulate that chaos, the very stuff that breaks FEM. It was a total game changer.
And at the heart of this revolution was an absolute legend, Ted Belichko at Northwestern University, who was also Professor Chen's advisor. This guy was a visionary, pure and simple. He comes up with the element-free Galerkin method, or EFG, which basically told the approximation, hey, you don't need to be tied to the mesh anymore. And then what he called his crazy idea for XFM. You want to model a crack? Don't remesh around it, just embed the crack inside the element. It was brilliant. Northwestern became the place to be for this stuff.
So if Belichko was the visionary who pointed the way, his student JS Chen was the master engineer who actually built the bridge. His work was absolutely critical. He took these promising, but sometimes shaky ideas and transformed them into solid, powerful, and reliable tools. Okay, so mesh-free methods had this one big nagging problem, the math behind them. These complex shape functions was a total beast to integrate. Now, there was a simple shortcut called direct nodal integration, or DNI, super fast, super efficient. The problem? It was wildly unstable. You'd get results that were complete and utter nonsense. And this is where JS Chen had his breakthrough moment. He developed SCNI, Stabilized Conforming Nodal Integration. It's an incredibly clever idea. He used a strain smoothing technique over these little nodal domains. What that did was filter out all the noise, all the instability, but it kept the speed and efficiency of DNI. It was the best of both worlds. SCNI is what really made mesh-free methods a reliable tool for the big leagues. So, all this talk of Galerkin methods, integration, variational principles, where did this stuff actually come from? Well, for that, we need to jump in our time machine and go way back to the giants of 18th and 19th century European science.
I mean, just look at this timeline. It's insane. In a span of less than 75 years, you have the graduation or doctorates of Euler, Lagrange, Laplace, Gauss, and Poisson. It's like the scientific equivalent of an all-star team, just an unbelievable concentration of genius. And the math they invented, often for things like astronomy or pure theory, ended up being the foundation for everything we do in computational mechanics today.
A huge piece of this puzzle comes from Euler and especially Lagrange. They completely reimagined classical mechanics. You know, Newton was all about forces, F equals ma. Lagrange said, let's think about energy instead. He came up with this idea that a system will always choose the path that makes its action stationary. And that single, elegant idea, the principle of stationary action, is the direct ancestor of the weak form that we use in FEM and mesh-free methods. It's a straight line from there to here.
Okay, next up we have Laplace and his brilliant student Poisson. Laplace is studying the motion of planets, and in the process, he develops this mathematical tool we now just call the Laplacian. Turns out that little operator is at the absolute core of the partial differential equations that describe, well, almost everything in physics. And then Poisson gives us his famous ratio. You know, when you pull on a rubber band, it gets thinner, right? Poisson's ratio is what quantifies that. It's a fundamental material property we absolutely need for any kind of realistic simulation.
And then there's Gauss. It's hard to overstate his impact. Let's talk about integration. Before Gauss, if you wanted to numerically integrate a function, you just pick a bunch of evenly spaced points. Gauss comes along and asks this unbelievably clever question. What if we could pick the perfect spots to evaluate the function? And by doing that, he created Gaussian quadrature. It's so accurate and so efficient that it literally became the engine inside almost every single finite element code on the planet. It's the gold standard. But wait, there's more. Gauss also gave us something that is, if you can believe it, even more fundamental to our story, the divergence theorem. So what does it do? On paper, it's a beautiful piece of vector calculus that relates what's happening inside a volume to what's happening on its surface. But for us, its true power isn't just the math itself, it's what it allows us to do. This theorem is the magic key. It's what allows us to do integration by parts, but in 3D. And why does that matter? Because it lets us take a strong form partial differential equation, which has to be satisfied perfectly at every single point, and transform it into an equivalent weak form integral equation. This new equation just has to be true on average over a small region, and that is something we can actually stop with a computer. So you see where this is going. This single theorem, from way back in the 19th century, is the launchpad for all Galerkin-based methods. It's the move that makes the finite element method possible. And it's the exact same mathematical step that underpins Professor Chen's SCNI. It is the crucial link in this entire intellectual chain. Okay, so we've traced the ideas back to 19th century Europe, but the chain doesn't stop there. The trail goes even colder, leading us back through the Renaissance to the Islamic Golden Age, a period where scholars weren't just copying old Greek texts, they were pushing the boundaries of knowledge themselves. Believe it or not, a key part of this lineage goes all the way back to the 11th century, to the Persian genius Ibn Sina, known in the West as Avicenna. He dared to challenge Aristotle's physics. He proposed this theory of impetus, or male, that when you throw something, you impart a quality to it, an inclination that keeps it moving. Now that might sound simple, but it was a revolutionary step away from Aristotle and a huge conceptual leap towards our modern ideas of inertia and momentum. Fast forward 200 years to the 13th century, and we meet another intellectual giant, Nasir al-Din al-Tusi. This guy was incredible. First, he establishes trigonometry as its own distinct field of mathematics. Then, he invents this incredible mechanism called the Tusi couple. It's this clever linkage that can generate perfect linear motion from two rotating circles. It showed an incredibly deep understanding of kinematics, and historians think it might have even influenced Copernicus centuries later. Okay, let's take a step back and look at the path we've traveled. We've gone from an 11th century Persian philosopher thinking about why a rock keeps flying, through the brilliant mathematicians of Enlightenment Europe, all the way to a cutting-edge research lab at Northwestern in the 1990s. It's one single, unbroken chain of knowledge. And this map here, this really visualizes that journey. It's this amazing web of professors and students, of ideas being passed down and built upon generation after generation. You can literally trace a line from Gauss and Lagrange down through the centuries to their academic descendants, which eventually leads you to Ted Belichko, and from him directly to JS Chen. It's over 1,000 years of intellectual inheritance, all right here. So let's just recap the whole journey. We started with Professor Chen's work on stable meshfree methods like SCNI. We traced it back through his advisor Ted Belichko, the meshfree pioneer, then back to Lagrange and Gauss, whose abstract mathematics became indispensable engineering tools, and finally back to al-Tusi and Avicenna, whose foundational work in kinematics and momentum set the stage for everyone who followed. It's an incredible story. So when we congratulate Professor Chen on this amazing, well-deserved John von Neumann Medal, we're really celebrating something much bigger than just one person's incredible career. We're celebrating this entire unbroken chain of discovery. His work is a perfect example of what scientific progress looks like. It takes visionary new ideas for sure, but it also takes the discipline and genius to build on the solid foundations of those who came before. And it just leaves you wondering, who's going to be the next link in this incredible 1,000-year chain?